fluids in tubes. Fluids in tubes problem. So imagine there is a U-tube like this. And there's water here. So this, in order to solve these kinds of problems, we're going to use that same equation that we just had. P is P atmosphere plus rho GH, right? Yeah. So then I can pour, let's say, alcohol in here and oil in here, different fluids of different densities, right? So let's say I have oil, 10 centimeters. Density is 0.7 gram per cubic centimeter. Density of water is 1 gram per cubic centimeter. Then I can have here alcohol. Density of the alcohol is, let's say, 0.8 gram per cubic centimeter. And then maybe on top of the alcohol, I have, let's make it, which one is the distance? Let's just say ish. There's one that is the distance. Some kind of fluid, let's just say. Oil fluid or something. So let's say that one has density 0.5 gram per cubic centimeter. 15 centimeters of that.
Gasoline.
Okay, so after it's all settled, this thing comes to equilibrium, what will the picture look like? So, how do you do problems like this? Okay, so it's kind of go like this, right? And see, it looks like here you have more fluid, and this one I'm not really sure what's going to happen, but we can assume something, and then if we get a negative answer, it means the opposite will happen, right? So at the beginning, you don't necessarily have to assume correctly. Let's assume that we're thinking this guy is going to go lower down, and all this is going to go up. Or let's say we assume this one is going to go down. It's probably true. This is going to probably go down, but it might be that it's not the answer. So that means at the end, the water is here, the water level. So it goes down, and of course this goes down with it. And then that goes down with it. So then you have here density is 0.5, and then here the density is 0.8. And then of course if this goes down, this water level will go up, right? So then it'll be here somewhere. Okay, this is the water. And then the oil will be here. .7 is the density, right? So what we can solve for is what? The difference in the water level, H. If we get a positive answer for H, that means my assumption is right. That means this water level will be at a lower height. If we get a negative answer for H, that means it's the opposite. This one will be up and this one will be down. You see? So then what's my argument going to be? My argument is going to be that this pressure here, the pressure here, and the pressure here should be the same. You see? Because they're both water, right? Because if the pressure here and the pressure here pushing down were different, then it would readjust itself, right? So at equilibrium, these two pressures here, P1 and then P2, they should equal, right? But then I'm going to argue what is P1. P1 is the pressure of the atmosphere here. P atmosphere, because I'm assuming, of course, the tubes are open at the top, right? So the pressure of the atmosphere plus the equation for that, right? So P1 is going to be P atmosphere plus density of oil, right, which is 0.7 times 9.8 times the height 10 centimeter. Now you might say in your mind, don't you have to convert 0.7 to kilogram per cubic meter and 10 centimeter to 0.1 meter? Not for these problems. You don't have to do the conversion. Why? Because it's going to end up that the pressure of the atmosphere is going to cancel, right? When this guy cancels, then this one can stay in centimeter and gram per cubic centimeter, right? And then what's the equation for P2? Then that's going to be the P atmosphere here plus its, right, P atmosphere. Oh, you know what? I needed to add here, I forgot. I need to go through the oil, then I need to go through the water, right? So I need to add the density of water there times gravity times H, right? Right? Okay, good. Then you're going to have here the pressure of the atmosphere plus the density of this fluid, which is 0.5 times 9.8 times 15 plus the density of this fluid, right? 0.8 times 9.8 times 8. And now we're going to set these two equal to each other, P1 equal to P2. Right? Well, when you set them equal to each other, the P atmosphere cancels. That's why it doesn't matter to convert. So set them equal, so 0.7 times 9.8. And of course, gravity will also cancel. And then you're going to have your 0.7 times 7 plus H equals 0.5 times 15 is going to be 7.5 plus 0.8 times 8 is going to be what? 6.4. H is equal to, and then subtract 7 from here. So that's going to be a half plus 6.4, 6.9 centimeter, and it was positive. That's it. Right? So this means that this guy will be a little bit below this level, right? The oil level here, 6.4, because this is 8. Cool. So these kinds of things, just do it like this. Set the two pressures equal to each other, and depending on what your assumption is, you just assume something. If it comes out negative, then you just reverse the direction. Okay, now let's do Archimedes' principle for floating objects and sinking objects. One of the most fundamental principles. So we'll do Archimedes' principle today, and then on Monday we'll finish up, the beginning of Monday we'll finish up with Bernoulli's equation. But over the weekend you should already be studying that, so you should always try to be a little bit ahead of it. But I'll do a couple examples of Bernoulli's equation, and then we can start with the traveling waves, chapter 16, study of waves and phase angles and all that good stuff, so the topics change again. Archimedes' principle. So Archimedes' principle is saying the general principle is that the buoyant force on an object, the buoyant force on an object is equal to the weight of the fluid it displaces. That's as short as I could try to make that. The buoyant force on an object is equal to the weight of the fluid it displaces. Or you could say takes up, the fluid that it takes up. And the fluid doesn't necessarily have to be liquid, it could be gas too. So take, for example, ourselves. We are immersed in the Earth's atmosphere. The Earth's atmosphere is a fluid. It's a gaseous fluid. We are displacing how much volume of gas? Since we are totally immersed in the gas, we are displacing a volume of gas equal to our volume. Right? Because if I wasn't here, the gas could occupy the volume that I'm occupying. So I'm kind of taking up the Earth's atmosphere space, you know. I'm saying, get out, I'm here, right? So how much volume of air am I displacing? Volume equal to me. So now the air is going to push me up with a buoyant force equal to the weight of that air. Okay, is that going to equal to my weight?
No.
No, because the density of air is a lot less than my density, right? So that buoyant force is not enough to lift me up. That's why I sink in air. That's why we're not floating objects, right? I sink, and I sink all the way down to the bottom of the air, which is the ground, right? Now, if I want to rise, what do? I could hold on to a bunch of helium balloons. What's that going to do? Like those really huge helium balloons. I might start to rise, right? What's happening there?
The amount of volume that they're taking up.
Yeah, so now the amount of volume they're taking up plus the amount of volume I'm taking up, we're a system. We become a system together, right? So now the air will push both me and that helium balloon up with a force equal to the amount of air we've displaced, right? Since the volume of the air is a lot more now, what happens? The force that they pushes up is much greater. My weight's still my weight, that hasn't changed. The balloon weight is not that much because the density of helium balloon doesn't weigh a lot, right? So my weight plus the balloon weight didn't go up a lot, but the volume of air that we displaced went up a lot, and so now the air can push us up with a force greater than our combined weight and we start to rise. So that's the idea of doing like a hot air balloon ride, right? You get inside of a basket. That's one of my bucket list stuff that I'm gonna do one day.
Yeah.
Hot air balloon rides.
Yeah, I went on that once.
Is it fun?
Really fun. They hit the air up, and then because the hot temperature, the density of the air, drops like pretty quick, and that's why
So what are you doing? You're basically heating up the air inside of the balloon.
Yes.
So then what happens?
Then the balloon just like kind of like raise up.
Yeah, the balloon, why are you heating it up? Well, you're kind of creating a helium type of gas that way. So what are you doing? The air in the balloon heats up and it starts to expand, but it can't expand because the balloon doesn't allow it to expand.
Yes.
So now the only way for it to expand is to escape from the inside of the balloon. When it escapes, what happens? The effective density of the air inside of the balloon goes down and acts like it's a helium.
Yeah.
All right? So why don't they actually use pure helium?
I recorded a video.
Huh? Yeah, probably. The other way would be just to blow pure helium in there. It's expensive and it might be combustible. I don't know, is it? But let's assume you didn't heat up anything, you just poured in helium gas. It might be dangerous, it might be combustible, I'm not sure. I know hydrogen
because,
is probably combustible.
The reason why it doesn't do that is because like, if you just pump in like helium, you cannot control the air inside. Like,
oh,
cannot, like,
that's true. So now if you want to go back down, what are you going to do?
You just keep and then you go to
that's
space
true.
and then you
That's true. So what for air, you can heat it up
and then or turn it off.
And then turn it off, the air comes back in.
Yes, like that.
Right,
That's
it gets
how
denser.
But they cannot control the direction, like where it goes or where it.
So were you kind of scared, like you didn't know where you were going?
We hit each other. Like,
yeah, did you hit someone else?
The balloon like hit each other, but that's okay. That's what they say. Like, that's okay.
You basically shake hands, hi, you hug, you know. That's nice. Yeah. So really, that's collisions, huh?
Yeah.
But it's never dangerous. Well, when you're colliding, the balloon is like this, doesn't the balloon first collide?
Yeah, the balloon.
So
first
you
collide.
don't actually
We don't
collide.
actually contact with the balloon.
Yeah,
We
okay,
don't
okay,
actually
I see.
contact.
Just the balloons collide.
Yes.
Is the dangerous part is what if they rip? And
Yes.
you collide
if
and they rip.
Then we, then we die.
Is there a danger in that?
That's okay.
Should I take that off my bucket list?
Combine
That's
with
okay.
skydiving.
You should try.
See, now he's talking me out of it as he's talking.
Bring a parachute, you can go skydiving at the same time.
Yeah. Now, the next bucket list is bungee jump off of a hot air balloon, right? You're right? Those are for the more crazy guys, right? Extreme guys. Okay, so now we have two cases. The density of the object is less than the density of the fluid. So those are the guys that will float, right? Floating objects. I guess we could put an equal sign here because if the density of the object is equal to the density of the fluid, it will kind of sink, but it will remain floating, right? And then any object, sinking objects would be if the density of the object is greater than density of the fluid. Okay? So then what's going to happen to floating objects? Well, floating objects, when you first put a floating object, let's say this is water, and let's say this is density of wood, so this is 1 gram per cubic centimeter, and let's say this is 0.4 gram per cubic centimeter. And so then what's going to happen? Initially, the weight of the object starts to make it sink, right? mg. So the dynamics of what's happening is gravity takes over and the thing starts to sink. But as it's sinking, it's displacing more and more water, right? It's starting to occupy the place of the water. And so now the buoyant force on the object is starting to get bigger, 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 right? Because it's displacing more as it's sinking. Well, there comes a point where it's displaced enough water, right, to where the weight of that water is equal to its own weight, right? So when it's floating finally, so you have FB equal to mg. So this portion of the volume that is sinking under the water, we can call that B prime, right? So that's how much water it will displace. It's equal to the portion of its own volume inside of the water, right? So now FB is equal to mg. When these two guys are equal, then it settles down and stops and floats at that point, right? So then what's FB? FB is equal to the what? The weight of the displaced water, right? Which is the density of the water times gravity times the volume of what? The portion of the object that's under the water. What's the mass of the object? The density of the object times gravity times what? The total volume of the object, right? So this is the density of the water, gravity times B prime, density of object, gravity times. So when they're equal, the object floats. So it's gravity, gravity cancel. So then what's the principle for floating objects? Floating objects sink all the way, not all the way, partially into the fluid that they're immersed until the amount of their volume inside of the fluid divided by their total volume is equal to the ratio of their densities. That's pretty much it. Okay? So how about if you have a let's say if this one was, we already said wood, right? If it was like a cubical, or not necessarily cubical, rectangular object, 8 centimeters by 4 centimeters by 3 centimeters, what would happen? then it would sink all the way down to what? How much of it would get wet? So if it's a rectangular looking object and 8 centimeters is the height, what portion of the height